Hello, this is Dr. Liu. In this video, I will explain what it means by conservation of energy. I also have a demo that I can play, so I can just get this set up. So here we have a skateboarder. So the skateboarder starts from here. So let's let go of the skateboarder. As you can see, is that a he or she? Well, that's probably a she with a ponytail. So she increases her speed or kinetic energy as she comes down from either side of this pipe, and then she decreases her speed or kinetic energy as she comes up. So now going up and coming down, and the pie chart has kinetic energy is green and potential is blue. So she's entirely blue on the top and then entirely green on the bottom. So that represents the energy exchange between kinetic and potential. They seem to be treating with each other. Here's some bar chart that describes the same thing. So potential goes up, kinetic goes down, potential comes down, kinetic goes up. So let's pause that. So to summarize this, energy is actually one of the most important quantities in nature, and the total energy of a system usually is conserved. There are some conditions, but let's think about this whole universe as one system that's not interacting with any other systems. So the total energy in the universe is a conserved quantity, which means there's just as much energy right now as there were some moment ago, or right after the Big Bang. So the energy has always been there, the same amount, maybe in different forms, maybe in different objects, and it transforms from one form to another, maybe it transfers from one object to another object, but it never gets destroyed, it never gets created. So this total is always the same. So think about this as maybe not a very good example of comparison. So think about water. Have a couple of beakers. So one beaker has water in it, and then you pour that water into the other beaker and pour it back and forth and back and forth. So assuming that you don't really spill any water and somehow there's also no evaporation, then the total amount of water always stays the same. So that is a way to describe energy conservation in a bit more solid way, because when we see matter, it's easy to understand that matter doesn't get destroyed or created unless somehow we do some sort of maybe chemical reaction, maybe physical reaction to turn matter into some other matter. This is an easy way to visualize energy, is to have water or these bar charts, and they go up and come down. So this total, which is in this kind of yellowish brown color, is always constant, and this is not exactly the entire experience that we feel, because we actually have friction, right? So if we add friction to our system, just put it in the middle. So what happens here is, as the skateboarder goes back down and up, she has friction between her skateboard's tiny little wheels and this track. So the total kinetic plus potential energy will start to drop, and the thermal energy due to that friction doing work will grow, but the total still stays the same. So let's just unpause her. So let's thermal energy start to grow, and we have this from everyday experience. So if you come down a half pipe and say you don't fall, you just keep skateboarding up and down, what happens is you end up on the bottom, not moving at all. So that is the situation I'm simulating right now, because of the existence of friction and probably also air drag. Let's just call that all together the friction term. And you can see this will take a while, right? Because the slower you go, the possibly less friction you feel as you're going at relatively high speed on the skateboard. So now she's almost stopped. So we can kind of wait, but this is pointing to the point where she kind of stops. Okay, so I guess there's no more motion. she turned all her energy, kinetic plus potential, into thermal, and her total is still the same. We call this sum of kinetic and potential energy a different term. We call that a mechanical energy because this is mechanical in nature. There's motion of objects, and there's also height change, right? Potential due to gravity, and you can also add potential due to springs. These are all mechanical things. There's nothing such as electrical or chemical or nuclear in nature. So the sum of all these different mechanical related potential energies and kinetic energy, I would say energies, because there's potentially a rotational kinetic energy compared to this what we can call translational kinetic energy. So let's go back to the main page here, and I want to say that energy is conserved in a very in a general way. When does energy stay conserved? Well, if there's no external force, or I'll use this symbol, net of the external force. That means there are some external forces, but you add them together into a total, or the total add to zero, then it's conserved. We discussed this in a little bit, what energy, how energy gets transferred, right? That is because of work. If there's no external force that does work or transfers energy into a system or out of a system, then the energy in the system will be kept, maintained, including thermal. If you include the entire track or the half pipe and maybe the surrounding air. So we have to be careful with the system, because if we forget to count the track and the air surrounding it as part of the system, we start seeing there's less and less energy every time the skateboarder comes down the pipe, because that thermal energy heats up the pipe and also the air surrounding it. And if we're not including those in the system, we just end up miscounting the total energy and say that total energy seems to dwindle, which is not right. Well, it's really hard. You think about that, counting all that energy in the surrounding air. Is that even possible? There are systems that are isolated enough, so it's quite possible. But other systems, such as things, people near us, they're not that isolated. So another thing that we can use is to specify what type of energy within the general sense of all energies. We call that mechanical energy, we just discussed, right? Mechanical energy. So we sometimes just use this E, mechanical. And it is a sum of kinetic energy, and you can use KE if you want, plus a few potential energies. This is potential energy due to gravity, and here's the potential energy. I use SP for spring. This is that potential energy due to a spring. This is pretty much it for the moment. Kinetic energy only has translational kinetic energy because we don't really know exactly how to describe rotational kinetic energy yet. So this whole thing is called mechanical energy. And mechanical energy is just a subsection of the total energy, such as thermal energy not included, right? And there's also other type of chemical, right? Chemical, nuclear, electrical potential energies are not included. So in order for this to be conserved, we need to apply more stringent rules. So besides this external force doing no work, we also have to have forces, internal forces that are conservative. So let's spell this out. Mechanical energy conservation. Conservation of mechanical energy. Oops. So net external force is 0. That means external forces do not do work. Okay, so what else? There's also internal forces. They're all conservative forces. Okay, so there are a few things I want to specify. What is internal force? What is the system anyway? And then what is a conservative force? Okay, so internal force. This really depends. Depends on what your system is. For example, that system with the skateboarder and, well, we didn't say and, we just said the skateboarder, but we actually should have an and, the skateboarder and the earth, right? So without the earth, she wouldn't be coming down at all, so there wouldn't be any exchange of kinetic or potential because there wouldn't be potential due to gravity. So this internal force requires us to be more carefully counting what's included in our system. So in this example of skateboarder, let's redo that. Is let's say skateboarder plus earth. Let's keep like that. So the earth and skateboarder are both included, which means the force between them, the gravity, is not external force. So the requirement of the external force being 0 or doing no work, it does not apply to gravity. So this gravity, and sometimes written as weight, right, is internal. Because now it is the force between these two parties, right? The skateboarder and the earth. So it is internal. And what other force can be internal? Well, let's think about this. There's no other forces between these two. So let's enumerate external force. Friction could be external. And so can normal force be. And what about the conservative forces? Well, Fg, gravitational force, is conservative. And friction, normal force, or this Fn, whichever you prefer, are non-conservative. Well, wait a second, can we not apply the mechanical energy conservation anymore? Well, here, if friction is 0, then okay, it doesn't do work. So no work. Work from friction, right? And also, we didn't really talk about this. We have to be a bit more specific, although I wouldn't have to do it every time. The tracks are rigid, right? Which means normal force is always perpendicular to the direction of motion. So this means this normal force is perpendicular to direction of motion, which causes normal force to do no work. So if this force does not do any work, okay, you can count it out. And this force, well, we didn't include friction for some of our simulations, so that could be counted out. So which means if friction is 0, then our mechanical energy is conserved. If friction is not zero, then our mechanical energy is not conserved. Just like what I showed, the mechanical energy is here is dwindling. This total here is mechanical energy, and we had friction on. So see here, potential energy, the blue bar, and that total energy, that brown yellow brown bar, they're the same height. But as soon as I let go, the total is going to change. It's going to get less. Let's run. As thermal energy builds up, right? So looks like in their simulations, thermal energy is increasing the greatest at the greatest speed. So that's always at the bottom of the track, and potential energy is zero. Kinetic energy is largest, and that's where thermal energy increases the most quickly. So if you turn thermal energy friction to zero, as you can see, thermal energy no longer increases, and this total will be the same. So this is almost a quarter of that energy lab. You can see green is kinetic and blue is potential. So it's just all green and into all blue and back and forth as we turned off the friction simulation, right? So in this case, energy is conserved, and as you can see, the outcome is not exactly realistic, and is also very repetitive. So this tells you something. Although energy conservation seems very interesting, very important, it doesn't exactly tell you time. Which way does time flow? Does she come down or does she go up? And then she just repeats herself. But with this friction, you can pretty much tell which way time goes. It always goes into mechanical energy dropping, right? As a result of friction existing and doing negative work all the time at different rates, though. So you can see this pie chart start closing off as mechanical energy is turning more and more into thermal, although the total doesn't change, right? The energy conservation doesn't tell you which way things should go or events should happen. But as you add thermal into the system, you can pretty much tell she was supposed to start at the top, or maybe either top, and she's supposed to come down and eventually gets all of her mechanical energy turned into thermal. So that tells you which way time flows. It doesn't go backwards, right? She cannot somehow just pick up all that dissipated and dispersed thermal energy, somehow just springs up to the top of that track. That never happens. So back here, I want to do a few more things. Conservative force. So what forces are conservative? I just said gravity was conservative, and also this spring force is conservative. And in our examples, we do not cover any more. And other forces, this one is conservative, but we don't really use it at this level. This is universal gravity, which is the reason of having gravity near the surface of Earth is universal gravity. So these are the only forces that are actual forces and conservative at the introphysics 1 level. There are other conservative forces in introphysics 2, such as, let's put a semicolon here. So this is electrostatic force. That could be a conservative force as well. So there are very few conservative forces, and other forces are non-conservative. And there's one force that's kind of special. It's static friction. We can touch upon that in the rotation chapter. And what it does is it does something interesting. It takes some rotational kinetic energy and turns into translational kinetic energy, or the other way around. So think about how your car accelerates. You're not pushing it, right? The car doesn't push itself; it cannot. So what it does is it pushes against the ground, the asphalt, and the asphalt pushes forward. So that is a static friction. Hopefully, it's static, right? Otherwise, your wheels just slip, right? So let's imagine you're accelerating slowly under fine road conditions. Then static friction pushes you forward, And without static friction, say if you just jack up your car and you can see your wheels are just turning, so rotational kinetic energy. With friction, some of that rotational kinetic energy turns into your entire car's translational kinetic energy. So it's an interesting way of using frictional force to do that without actually losing any energy, as long as the frictional force is static. So there's no relative motion to cause any translation. If there's a translation, then there's some kinetic friction, which is not conservative. So let's put S here, conservative forces. So there's only a very few. All right. So in the next video, I will start explaining how to use conservation of energy in order to solve problems. So let's see it firsthand how to use it in theory. So conservation of energy would mean we're actually mostly just doing mechanical, right? So mechanical energy 1, this will be a total of the mechanical energy at a certain point in time is equal to mechanical energy 2. This is at a later point in time. We assume these two are equal if the conservation conditions are met. So this is basically a single equation that we can get if mechanical energy is conserved. So with equations come solutions, right? So this one equation gets you one solution, or one question gets answered. So we'll talk about that in the next video. Thank you.